In the cold dark beyond our solar system, a tiny red star burns just over 4 light-years away, and reaching it would still take longer than human civilization has existed. You think space is close. You are wrong. We are about to fly past a star that erupts with flares 100 times stronger than ours, a planet baked by invisible fire, and a journey so long that 2,700 generations would die on the way. Hit subscribe if cosmic distances thrill you. Brace yourself. We begin. Look up at the southern sky on a clear night, and somewhere in the constellation of Centaurus, hidden behind a brighter pair of stars, sits the closest stellar neighbor we will ever have. Its name is Proxima Centauri. The word Proxima literally means nearest, and that single word has fooled humanity for over 100 years. Because nearest, in cosmic terms, is a cruel joke. Proxima Centauri sits about 4¼ light-years away from Earth. That sounds almost friendly. 4 years of something. We finish college in 4 years. We pay off cars in 4 years. We can plan 4 years ahead. But this is not 4 years of driving. This is 4 years of light. And light is the fastest thing the universe allows to exist. A single beam from Proxima, racing toward your eyes at over 670 million miles per hour, takes more than 4 years to land on your retina. 4 years of pure, uninterrupted, unimaginable speed. Now ask yourself a question. How fast can a human go? The answer is humbling. The fastest object our species has ever built, the Parker Solar Probe, screams across space at about 430,000 kilometers per hour. That is roughly 690,000 kilometers per hour. It is so fast that if you launched it from New York, it would reach Tokyo in under 1 minute. It is the closest thing to a real spaceship we have, and it is still slower than light by a factor of about 1,600. Picture that gap. Picture a freeway where every other car is moving at the speed of sound, and yours is a bicycle. That is roughly the ratio between human technology and the speed of light, and the speed of light is the only speed that makes 4 light-years sound short. Here is the picture nobody draws. Imagine a single grain of sand sitting on your kitchen table. Now imagine the next grain of sand placed in a city on the other side of the planet. That is roughly the spacing between stars in our galactic neighborhood. Empty space. Stunning, terrifying, almost holy emptiness. And Proxima is the closest grain. This is where the trick of language breaks down. When astronomers say nearest, they mean nearest by a system that ignores how slow we actually are. They are speaking from the perspective of photons and parallax measurements. From a human perspective, from the perspective of bodies that need food and air and sleep, Proxima Centauri is not nearby. It is functionally on the other side of forever. And it gets worse. Because Proxima is not standing still, it is orbiting the center of the galaxy at hundreds of thousands of miles per hour, in a slightly different direction than we are. So even if we built the ship of our dreams today and aimed it perfectly at the star, by the time we arrived, Proxima would no longer be where we aimed. We would have to lead the target, like a quarterback throwing to a receiver running across the field at relativistic speeds. You are starting to feel the weight of the problem. Good, because the next chapter shows what happens if we tried to make the trip on foot. Pretend for a moment that you decided to walk to Proxima Centauri. Forget physics. Forget that there is no air, no ground, no gravity to push against. Just imagine in some impossible cartoon universe that a sidewalk stretched from your front door all the way to the surface of the nearest star. You pack a bag, lace up your shoes, and begin a steady walk at 3 miles per hour. How long until you arrive? Roughly 950 million years. Pause on that number. Not 900, not 9,000. 950 million years. To put that into perspective, the entire history of multicellular life on Earth is shorter than that. When you took your first step on this imaginary sidewalk, the most complex creatures on this planet would be tiny soft worms and sponges. By the time you finally reached Proxima, mammals would have come and gone, Dinosaurs would have risen and been wiped out by an asteroid, and an entire civilization of humans would have built cities, written poetry, sent rockets, and disappeared. You would still be walking. Now speed up. Drive a car at 60 miles per hour, 24 hours a day, with no stops, no fuel breaks, no traffic. The trip still takes around 48 million years. A jet airliner cruising at 550 miles per hour gets you there in about 5 million years. These are not numbers for the human imagination. They are numbers for geology. Try a faster machine. The space shuttle, when it was alive, orbited Earth at around 17,500 miles per hour. That sounds blistering. It is fast enough to circle our planet in 90 minutes, but pointed at Proxima, the shuttle would need around 160,000 years to arrive. 160,000 years ago, our ancestors were just beginning to leave Africa. Anatomically modern humans existed, but writing did not, farming did not, cities did not. Now imagine that voyage in reverse. A shuttle launched at the dawn of our species would only be arriving at Proxima Centauri right about now. This is the part where the brain rebels. It wants to invent a number that feels comfortable. 40 years maybe. A century. Something a person could survive. But the universe does not negotiate. The distances are what they are, and the speeds we possess are what they are, and the product of those two facts is measured in geological epochs. There is one trick that helps. Astronomers sometimes compress the entire scale of the cosmos onto a model where the star we orbit is the size of a basketball. On that scale, Earth becomes a pea floating about 90 feet away, and Proxima Centauri, on that same scale, Proxima sits about 5,000 miles away in another country, on another continent. A basketball in one city and another basketball thousands of miles away, with absolutely nothing in between except a vast ocean of black. That is the real picture. Not friendly, not nearby. A distance so cruel, it laughs at human time. And yet somehow we have managed to send actual machines partway into that black void. Slow machines, patient machines. The next chapter checks in on the fastest ones we have ever launched. And the news is not good. In 1969, 3 men climbed into a thin metal can on top of a 36-story tower of explosive fuel, and a few days later, 2 of them walked on the moon. To this day, the Apollo program is considered the single greatest engineering achievement in human history. The spacecraft that carried those astronauts, the Apollo Command Module, traveled at speeds reaching about 25,000 miles per hour on its return from lunar orbit. For a brief moment, those 3 Americans were the fastest humans who had ever lived. So how long would Apollo take to reach Proxima Centauri? About 43,000 years. Let that breathe for a moment. The single most ambitious crewed mission in our species' history, the gold standard of speed and engineering, would still require a journey twice as long as the time since the last ice age. If an Apollo-style ship had been launched at the height of cave painting in southern Europe, it would only be arriving at Proxima right about now. And here is the cruel detail nobody mentions about Apollo. That 25,000 mile per hour figure was a peak speed achieved during re-entry, not sustained cruise. The actual outbound journey to the moon happened at much slower speeds because the spacecraft was constantly fighting Earth's gravity, then slowing down for the moon. A real Proxima mission would need to maintain enormous speed for years, decades, centuries. Apollo's engines could not have run that long. They burned for minutes. Total firing time across the entire mission added up to less than a single afternoon. So forget Apollo's peak speed. The honest comparison is the average speed needed to make the trip in a human lifetime. To reach Proxima Centauri in 80 years, a ship would have to cruise at roughly 5% of the speed of light. That is around 33 million miles per hour. Apollo was 1,300 times slower than that. Think about what that ratio means in everyday terms. Imagine being asked to row a small boat across the Atlantic Ocean. except the boat moves 1 inch per hour. That is the same kind of mismatch. The technology works, the distance simply ignores it. There is another problem nobody talks about at backyard barbecues. Apollo carried 3 people for about 8 days. Their air, water, food, and waste systems were sized for that exact mission. Stretching the same kind of life support to a 43,000-year journey is not a matter of packing more sandwiches. It is a complete rebuild of physics, biology, and engineering. Every gasket, every wire, every piece of plastic on Apollo would have crumbled to dust thousands of times over before the ship reached its target. And yet, despite all of this, Apollo remains an interesting baseline, because if our greatest crewed achievement gets us nowhere near the nearest star, then the question stops being about engineering. It becomes a question about ambition. Humans have walked on the moon. Humans have landed robots on Mars. Humans have flown probes past every classical planet in this system. Every one of those missions counted in days, months, or years. Proxima counts in millennia. The leap is not linear. The leap is a wall. The probes we have launched feel the wall most clearly, and the next chapter visits the 2 ghost ships still drifting through the black. Right now, as you read these words, 2 human-built objects are quietly drifting through interstellar space. They have been traveling for over 48 years. They have crossed the orbits of every classical planet. They have left the heliosphere, the bubble of charged particles that wraps our solar system. And they are, by every meaningful measure, the farthest things our species has ever made. Their names are Voyager 1 and Voyager 2, both probes launched in 1977, just 16 days apart. Voyager 1 is now cruising away from us at about 38,000 miles per hour. That is roughly 17 kilometers per second. It is faster than any rifle bullet, faster than any plane, faster than almost anything humans have ever set in motion. If Voyager 1 were aimed straight at Proxima Centauri, it would take over 73,000 years to arrive. But here is the twist. Voyager 1 is not aimed at Proxima, neither is Voyager 2. Both spacecraft are flying in completely different directions, on trajectories chosen to use the gravity of giant planets as slingshots. The decision was made because, in the 1970s, going to Proxima was so absurd that nobody even tried to point a probe at it. The engineers picked the gas giants instead, because those were destinations a human team could actually reach in a working lifetime. So the 2 fastest objects we have ever launched are wandering through the galactic suburbs on courses that will never come near Earth's nearest star. What will they do instead? Drift, forever, in any meaningful human sense. Voyager 1 will pass within about 1.5 light-years of a faint star called Gliese 445 in roughly 40,000 years. Voyager 2 has its own unremarkable flyby of a different star, AC plus 793888, around the same time. Both encounters will happen long after every human alive today is dust, long after every language now spoken is forgotten. There is a beautiful and brutal detail here. Each Voyager carries a golden record, a phonograph disc loaded with greetings in 55 human languages, photographs of life on Earth, music from Bach to Chuck Berry, and the recorded sound of a kiss. Carl Sagan helped design it. The records are coated in gold to survive cosmic radiation, and they are projected to remain readable for over 1 billion years. 1 billion years is a very long time to send a message, and the message will probably never be read. Because here is what the Voyagers actually tell us in their slow, patient drift. They tell us that even when humans go all out, even when we throw the full weight of NASA's budget at deep space, the result is a 38,000 mile per hour crawl. We did not build a galactic vehicle. We built the fastest dinghy possible, and we set it loose in an ocean so wide that the dinghy will never reach the next shore. That is the honest legacy of the Voyager program. Stunning, heartbreaking, and embarrassing all at once. But there is one machine that goes faster than Voyager, much faster, a probe so quick it sets records every time it loops past the brightest star in our sky. And even it cannot save us. The next chapter explains why. Imagine an object so fast that it could cross the United States from coast to coast in under 30 seconds. An object so fast that it travels the entire distance from New York to Los Angeles in less time than it takes you to read this sentence. This machine exists. Right now, it is real. It is the Parker Solar Probe. Launched by NASA in 2018, Parker was designed for one purpose: to dive into the outer atmosphere of the closest star to Earth, the one we orbit every year. Yes, the one we are not naming. To do this, Parker uses repeated gravity assists from Venus to whip itself into faster and faster orbits, plunging closer and closer to the surface. On its closest passes, Parker reaches roughly 430,000 miles per hour. That is around 690,000 kilometers per hour. It is the fastest object humans have ever built. If you pointed Parker straight at Proxima Centauri and let it fly at that peak speed, it would arrive in around 7,200 years. This is a stunning improvement. Voyager would take 73,000 years, Apollo would take 43,000 years. Parker cuts the journey by a factor of 10. For one shining moment, you can almost feel hope. 7,000 years is still a vast number, but it is a number that fits inside the recorded history of human civilization. Ancient Sumerian temples were being built about 7,000 years ago. If a Parker-class ship had been launched at the founding of the first cities, it would be arriving at Proxima right about now. But hope dies fast, because Parker only reaches that speed at the bottom of its dives, in tight loops around its target. The probe cannot keep that speed in a straight line for 7,000 years. It does not carry the fuel. It does not even carry an engine designed for sustained thrust. Parker is a glorified planetary moth, beating its wings around a single flame. Take it out of that flame, and it slows. There is a deeper lesson here. Parker is fast because of a star, not because of a rocket. The energy comes from looping around a massive gravity well. Once you leave the gravity well, you keep the speed, but you stop adding more. A real Proxima mission would need to accelerate continuously for years, decades, perhaps centuries. No chemical rocket can do that. We do not have enough fuel. We do not even have a container that could hold enough fuel. To put it in everyday terms, imagine a swing set. You can pump your legs and go higher and higher, faster and faster. But if you ever jump off the swing, your top speed is fixed. You cannot keep accelerating in the open air. Parker is a swing rider who jumped off at her highest point. She is incredibly fast for a moment. She is also coasting forever. So Parker, the fastest machine we have ever made, would still need an entire span of human civilization to reach the nearest star. And it could not even sustain its speed. The math is humiliating. There is one thing in our universe that travels faster than Parker by a factor of more than 1,600. The next chapter looks at what that thing tells us about distance itself. Light is the speed limit of the universe. Nothing with mass can match it. Nothing with information can beat it. Photons are the only things that travel as fast as the laws of physics allow. And even light, the absolute fastest thing in existence, takes more than 4 years to reach us from Proxima Centauri. Try to feel that. A single photon launched from the surface of Proxima today will not arrive at Earth until 2030. That photon will travel at 670 million miles per hour, every second, every minute, every hour, without slowing, without stopping for over 4 straight years. By the time it lands on a telescope mirror, infants alive now will be in elementary school. Smartphones still in factories today will be in landfills. Songs not yet written will have already topped the charts. The light you are seeing tonight when you look at Proxima is not how Proxima looks. It is how Proxima looked 4 years and 3 months ago. You are looking at the past. Now flip the direction. If humans on Proxima b sent a radio message to Earth at this exact moment, the message would arrive in early 2030. If we answered the same day, our reply would arrive at Proxima around 2034. A simple hello and how are you conversation would take over 8 years. Just one round-trip exchange. That is the light-speed conversation. It is the fastest possible chat in the universe, and it spans an entire span of childhood. The reason this matters is not just trivia, it is the deepest possible limit on what nearness even means. When the universe itself, working at maximum legal speed, still needs 4 years to cross a gap, that gap is enormous. There is no shortcut. There is no faster route. There is no clever physics that gets a normal object across faster than light. Wormholes remain mathematical guesses. Warp drives remain pure theory. The fastest information channel we have is a beam of photons, and that beam still pays a 4-year toll. Here is a way to picture it. Imagine the universe as a giant city. The street between you and Proxima is one straight road. Every other vehicle in the city, no matter how fancy, has to obey a speed limit. Light is the only thing allowed to drive at that maximum speed. Every spacecraft you ever build will be slower. Every probe, every rocket, every starship in every science fiction movie ever made is, by the laws of nature, slower than light. So if light takes more than 4 years, your ship takes longer. Always. This is what makes nearest feel like a curse. Even the universe's own messenger needs years to cross the distance, and the closer you look at the star at the other end of that beam, the stranger it gets, because Proxima Centauri is not a calm, gentle neighbor. It is a small, angry, flickering thing, and a lot of what we have learned about it should keep future astronauts awake at night. The next chapter starts where the trouble really begins. We zoom in on the star itself, and we find out that nearby does not mean familiar. Pure distance is hard for the human brain. Numbers above a few thousand turn into mush. So before going further into Proxima itself, here is a chapter dedicated to one single number, written out in different ways, until the size of it finally lands. Proxima Centauri sits about 25 trillion miles from Earth. 25 followed by 12 zeros. If you wrote that number on a sheet of notebook paper, the zeros alone would take up almost a whole line. Now consider what a trillion really is. A million is roughly the number of seconds in 11.5 days. A billion seconds is about 32 years. A trillion seconds is almost 32,000 years. 25 trillion seconds is around 800,000 years. So if you started counting 1 mile per second, 1 mile every single tick of the clock, no breaks, no sleep, you would reach Proxima in around 800 millennia. Try a different approach. The circumference of Earth at the equator is roughly 25,000 miles, so Proxima sits about 1 billion Earth trips away. If you flew around the planet at the equator one full loop every single day, never resting, you would still need about 2,700,000 years of non-stop flying. Try another. The average commercial passenger jet flies at around 550 miles per hour. If you boarded that plane right now and the pilot pointed it at Proxima, the trip would take roughly 5 million years. Try one more. The fastest human pulse, sprinter heart rate at full effort, is around 200 beats per minute. That is 1 beat every 300 milliseconds or so. To beat your heart 25 trillion times at that maximum sprint rate, you would need around 238,000 years. And those are just heartbeats, not miles. Your blood would have to push past the rim of the solar system roughly 30,000 times to add up to a single Proxima distance. This is the trick of cosmic scale. The brain looks at a sky full of stars and says, "Oh, those are basically right there." The brain is wrong. The sky is a flattened map. Up there, in the actual three-dimensional volume of space, every twinkling dot is separated from every other twinkling dot by oceans of mostly nothing. And the closest twinkling dot to us, the one our astronomers call Proxima because it is the closest, still sits 25 trillion miles away. There is one more way to feel it. take a single sheet of paper and place a dot in the center. That dot is the star we orbit. Now ask yourself, where on that paper should you place a second dot to represent Proxima? The honest answer is, you cannot. Not on a sheet of paper, not on the side of a football stadium. To draw the two stars to scale with a millimeter dot for ours, you would need to place the second dot roughly 20 miles away. 20 miles, between two specks the size of pinheads. That is what nearest means in our galaxy. That is the gap our descendants are trying to cross. And the destination at the other end of that gap is no warm, welcoming hearth. The next chapter turns up the dials and looks at the star itself. Step outside on the darkest night you can find, away from city lights, away from highways, somewhere a long way from anywhere. Look up at the constellation Centaurus, which hangs low in the southern sky for most people in the northern hemisphere, and high overhead for stargazers below the equator. Find the bright pair known as Alpha Centauri A and B. Just southwest of that pair, roughly 2 degrees away, sits Proxima Centauri. Or rather, it should sit there, because you cannot see it. Proxima Centauri is too dim for the human eye. Even on the clearest night, in the darkest desert, with perfect vision, you cannot pick it out from the background sky without a telescope. The closest star to Earth, our nearest stellar neighbor in the entire universe, is invisible to us. That single fact is staggering. Astronomers had no idea Proxima even existed until 1915, when a Scottish astronomer named Robert Innes spotted it from an observatory in South Africa. A faint smudge, almost lost in the glare of its brighter siblings, sitting closer to Earth than any other star. Innes had stumbled onto our nearest neighbor in the cosmos, and he had to use a telescope to do it. Why so dim? Because Proxima is a red dwarf. Red dwarfs are the smallest, coolest, faintest type of normal star in the galaxy. They are the embers of the cosmos. Proxima has a mass of only about 12% of the star we orbit. Its diameter is roughly 1/7 the diameter of our home star, only about 1.5 times the width of Jupiter. If you placed Proxima where our local star sits, the sky would not catch fire. You would see a dim red bulb hanging in space, barely brighter than a full moon at midday. Some animals would still nap during what we now call afternoon. Its total energy output is around 0.16% of the brightness of our local star. Push that into the wavelengths our eyes actually see, and the number collapses to roughly 0.0056%. Almost everything Proxima radiates comes out in infrared, the invisible heat glow of a slow, dim ember. Here is an image that helps. Imagine standing in a vast, dark warehouse. Far away, near the back wall, someone has lit a single candle. That candle is Proxima Centauri. The walls of the warehouse are studded with floodlights, brilliant white spotlights of every color, and those are the giant blue and yellow and white stars elsewhere in the galaxy. Compared to all of that brilliance, our nearest neighbor is the candle, quiet, reddish, almost hiding. There is a strange comfort in this image. The closest star to us is also the shyest. It is not flashy, it is not famous. For most of human history, nobody even knew it was there. But that comforting picture is a lie, because as soon as astronomers turned modern instruments on Proxima, they discovered the candle has a temper, a violent, sudden, unpredictable temper. The little red ember can suddenly explode in brightness by a factor of thousands, in seconds, with consequences that would melt anything living near it. The next chapter watches the candle catch fire. Most stars are calm. They burn for billions of years with a steady, predictable warmth. Our local star, the one that powers life on Earth, has tantrums every now and then, sending out solar flares and coronal mass ejections that can knock satellites offline and dance auroras across the polar skies. But on the whole, it is a stable furnace, a reliable lamp. Proxima Centauri is not stable. Proxima is what astronomers call a flare star. That label sounds technical and harmless, The reality is closer to a fireworks factory on fire. Proxima erupts in violent, sudden flares, hundreds of times more powerful than anything our home star produces. These eruptions can multiply the star's brightness by a factor of 10, 100, sometimes thousands, in a matter of seconds. The reason has to do with the structure of red dwarfs. Larger stars carry their heat outward in two zones, a deep radiative layer and a shallower convective shell. Red dwarfs do not bother with two zones. They are fully convective, all the way down. Hot plasma rises, cool plasma sinks, and the whole interior churns like boiling soup. That violent churning twists and tangles the star's magnetic field. The field stores enormous amounts of energy. When the lines of force suddenly snap and reconnect, that stored energy unloads in seconds, in the form of a flare. For a person standing on Earth, this is interesting trivia. For anything living on a planet orbiting Proxima Centauri, it is the difference between life and a sterilized rock. In 2016, astronomers caught Proxima erupting with a flare that briefly increased its ultraviolet brightness by over 10,000 times in a fraction of a second. If humans could see ultraviolet light, it would be like being blinded by the flash of a camera. 2 years later, an even larger flare was recorded, with a peak brightness around 10 times stronger than the strongest flares our local star has ever produced, at similar wavelengths. Researchers using the ALMA Radio Observatory and the Hubble telescope reported a flare in 2021 that was about 100 times more powerful than typical flares from our home star. To picture it, imagine someone standing in a dim room with a small flashlight. You can look directly at the bulb without hurting your eyes. Now imagine that flashlight, in less than a second, suddenly becoming as bright as the front headlight of an oncoming truck on a fog-free highway. Then back to a flashlight. Then back to a headlight, sometimes a stadium spotlight. Always unpredictable. That is what Proxima does on a regular basis. Here is the part that matters for human ambition. If we ever send a probe to Proxima, that probe will spend its entire approach being washed in radiation pulses dozens of times more intense than anything ever survived by an Earth-based satellite. If we ever send people, those people will live their lives, raise their children, and grow old beneath a star that occasionally flashes hot enough to fry electronics in seconds. There is a small mercy in this picture. Most of Proxima's flares last only seconds, sometimes a few minutes. They are violent but brief. The atmosphere of a sturdy enough planet might shrug off any single eruption. The trouble is, the flares never stop, and the next chapter shows what one record-breaking blast did when scientists finally caught one on camera. May 1st, 2019, a small team of astronomers was looking at boring archive data from the ALMA radio telescope, hoping to find a faint dust ring around Proxima Centauri. They were not searching for excitement. They were doing routine science. They were about to find one of the most violent stellar events ever recorded in the modern era. Buried in the data was a single moment in time when Proxima Centauri had simply lost its mind. In a span of seconds, the star erupted in a flare estimated to be roughly 100 times more powerful than any flare ever produced by our local star. The total energy released in that brief blast would have lit up the entire Earth-facing side of any nearby planet, with hard radiation across the spectrum. Ultraviolet light spiked by orders of magnitude. Radio waves screamed across nearly the entire range that ALMA could see. For a flicker of time, Proxima was a different kind of object entirely. The team, led by an astronomer named Meredith McGregor, published the results in 2021. Her quotes are unsettling. If there was life on the planet nearest to Proxima Centauri, it would have to look very different than anything on Earth, McGregor said in the statement. Translation: anything alive nearby would either be living deep underground or built out of biology Earth has never seen. To understand why this flare was so important, picture a normal solar flare from our home star. At its peak, it doubles or triples the star's ultraviolet output, briefly, in a tiny region of the disk. strong enough to disrupt radio communications and damage satellites. Now multiply that by 100. That is what Proxima did in 2019. And not as a once-in-a-billion-years event, as something that may happen often enough to actually matter on geological timescales. What does that mean for a planet sitting in Proxima's habitable zone? It means an ozone layer, if one ever forms, gets stripped away faster than it can rebuild. It means any atmosphere thick enough to shield a surface from radiation can be slowly chewed apart over the course of millions of years. It means liquid water, if it ever pooled on the surface, would be exposed to ultraviolet doses heavy enough to kill the hardiest microbes Earth has ever produced. A 2018 study using the Everyscope telescope array caught an even larger flare in optical light, a so-called superflare. The researchers estimated that ultraviolet light from this single event would have reached the surface of any nearby Earth-like planet with roughly 100 times the intensity needed to kill simple ultraviolet-resistant microorganisms. Now stack these events on top of each other, year after year, century after century, million-year cycle after million-year cycle. The star, our planet's closest stellar neighbor, turns out to be a relentless radiation bomb, periodically detonating in slow motion across a stretch of cosmic time. For a future human colony, the implications are brutal. You cannot live on the surface of a world being routinely bathed in radiation that strong. You hide underground. You build thick concrete shielding. You stop being a surface civilization and become a buried one. And even then, you are betting your descendants on a star that flashes without warning. But maybe there is still hope. Maybe there is still a world worth visiting. The next chapter looks at the planet itself, the one humanity has been quietly dreaming about. In August 2016, astronomers announced something that briefly made the entire planet excited. A rocky world had been confirmed orbiting Proxima Centauri. It was named Proxima Centauri b. It was roughly Earth-sized. It sat within the habitable zone, the band around a star where temperatures could, in theory, allow liquid water on a planet's surface. And it was the closest known exoplanet to Earth. The dream was instant. For the first time in human history, we had a real, confirmed, possibly Earth-like world within reach of the nearest star, the closest possible second home. Not a science fiction concept, an actual planet in an actual orbit, around an actual neighbor of the local star. Then scientists started looking more closely, and the dream began to crack. Proxima Centauri b has a minimum mass of about 1.06 times that of Earth. That is the good news. It is probably rocky, probably solid, probably the kind of place a future probe could land on rather than sink into. Its radius is estimated to be slightly larger than Earth's. Its orbital period is just 11.2 Earth days. That is short, astonishingly short. A single year on Proxima b passes in less time than it takes most people to get a haircut and finish a work week. Why is the year so short? Because Proxima b orbits incredibly close to its star. The planet sits at roughly 5% of the distance between the Earth and our local star. Proxima Centauri b orbits its parent star at a distance of about 0.04848 ATU, 7.253 million kilometers, 4.506 million mi, with an orbital period of approximately 11.2 Earth days. It is more than 20 times closer to Proxima than Mercury is to our home star. If you placed Proxima b in our own solar system, it would be deep inside our local star's atmosphere, vaporized in days. Wikipedia. So why is it not vaporized around Proxima? Because Proxima is so dim. The star puts out so little energy that even at 5% of the Earth distance, the radiation at Proxima b's orbit is roughly comparable to what Earth gets from our own star. Temperatures, in theory, could support liquid water. In theory. Reality bites, because being that close to a flare star means the planet is constantly bathed in ultraviolet light and high-energy particles hammered every time the star throws a tantrum. the same flares that look fascinating from a distance hit Proxima b like a flame at a moth. There is no shielding distance, no inverse square law mercy. The planet is in the line of fire. Here is the picture. Imagine standing next to a campfire on a cold night. You can stand a few feet away, warm and comfortable. Now imagine the fire occasionally bursts into a 5-story bonfire for 30 seconds, then drops back to embers. Sometimes a few times an hour. That is what Proxima b's orbit feels like in terms of radiation. Comfortable on average. Lethal in spikes. There is more bad news. Because Proxima b orbits so close, it is almost certainly tidally locked, with one side permanently facing the star and the other forever in the dark. That single fact reshapes the entire concept of habitability. The next chapter walks across that strange world, where one side is locked in eternal day and the other in endless night. Imagine a planet where the star never moves. On Earth, the sun rises and sets. The seasons turn. Shadows shift across the ground hour by hour. Days come, nights come. And life has evolved around that rhythm. Sleep cycles, plant growth, ocean tides, the entire pulse of biology, all tied to the spin of our world relative to its star. Proxima Centauri b probably has no such rhythm. The planet is most likely tidally locked. That means the same face of Proxima b always points toward its star, while the opposite face always points into deep space. There is no day-night cycle as we know it. There is one half that is forever lit, and one half that is forever dark. Tidal locking is not a new idea. The moon is tidally locked to the Earth, which is why we always see the same face of it. The cause is gravity. A planet orbiting very close to a star feels enormous tidal forces, the same kind of stretching that pulls our oceans into bulges twice a day. Over millions of years, those forces drag the planet's spin to match its orbit, like a wheel slowly dragged into alignment with the axle. Once that lock sets in, it is almost impossible to break. On the day side of Proxima b, the star never sets. It hangs in the same spot in the sky. A dim red disk roughly 3 times wider than our local star looks from Earth. Anything on the surface would be permanently exposed to its red light, and during flares, to its violent ultraviolet bursts. The ground would never cool. The atmosphere, if there is one, would constantly churn upward as hot air rises and races toward the cold side. On the night side, the opposite extreme, the temperature plummets toward the freezing point of nitrogen. Stars wheel across a sky in which the local star is permanently absent. If you stood on the night side and looked up, you would see only blackness studded with distant suns. Liquid water would freeze rock solid. Any atmosphere that drifted over from the day side would condense, fall as snow, and possibly never thaw again. Now picture the strip in between, the terminator, a thin ring around the planet where the star sits permanently on the horizon, neither rising nor setting, just frozen at twilight. Some scientists think this thin band might be the only place on Proxima b where life could survive, warm enough to keep water liquid, cool enough to escape the worst of the radiation. Twilight forever. It is a haunting image, a ring of livable land circling a divided world, with infinite day on one side and infinite night on the other. Picture a sphere where every house has one wall facing a permanent red sunrise. Children grow up not knowing what an actual evening feels like. The star is always there, never going down, never going up, just hanging in the same place for the entire history of the species. There is one possible escape. If Proxima b has a slightly elliptical orbit, it might lock in a 3-to-2 resonance, like Mercury does around our local star. In that case, every other long orbit the planet rotates one full time relative to the star, and a slow day-night cycle returns. Hot and ugly, but not frozen on one side. The verdict is still open, but whatever Proxima b is, it is not Earth in a different sky. And the next chapter explains why the so-called habitable zone, may for Proxima be the wrong word entirely. Astronomers love the phrase habitable zone. It is one of the most powerful pieces of marketing in modern science. The phrase suggests a friendly band of orbit, a strip of cosmic real estate where life could comfortably exist. Pop science articles use it to imply that any planet in such a zone is a candidate Earth. Press releases attach the phrase to almost every new exoplanet discovery that might support liquid water. For Proxima Centauri b, the term is, at best, misleading. At worst, it is dangerous. The traditional definition is simple. A habitable zone is the range of distances from a star where the temperature on a planet's surface, given a reasonable atmosphere, allows water to stay liquid. Too close to the star, and water boils away. Too far, and it freezes solid. The Goldilocks zone, as it is sometimes called. Just right. Proxima b sits in that just right band. By that one criterion alone, it is habitable. But habitability is not just about temperature. It is about pressure, atmosphere, magnetism, radiation, chemistry, stability, and time. Earth survives because our planet has a thick atmosphere held in place by a strong magnetic field, both of which protect the surface from charged particles streaming off our local star. Strip away the atmosphere or kill the magnetic field, and life on Earth ends. The planet would still be in the habitable zone. It would just be a sterile rock. Proxima Centauri b probably does not have the protection Earth has. The first problem is the magnetic field. Tidally locked planets rotate very slowly relative to space. A slowly spinning iron core generates a weak magnetic field. A weak field is a leaky umbrella. Charged particles from Proxima's stellar wind, much fiercer than the wind from our own star, would punch through that field and reach the upper atmosphere unhindered. Over millions of years, the lighter molecules in the atmosphere are stripped away. Hydrogen first, then water, then everything else. The second problem is the flares. Each major eruption from Proxima delivers a pulse of ultraviolet light and high-energy particles that batters whatever atmosphere remains. Without a strong magnetic shield, the particles drive chemistry that destroys ozone-like protective layers and accelerates the loss of light gases. Over time, the atmosphere thins, the water boils off, the pressure drops to nearly nothing. The planet ends up looking more like Mars than Earth. The third problem is the lopsided heat balance. If the day side is permanently roasted and the night side permanently frozen, the atmosphere may collapse entirely. Gases freeze out on the cold side and stay there. The planet ends up with a thin smear of atmosphere on the boundary and nothing else. Stack all of this together, and the so-called habitable zone around Proxima Centauri starts to feel less like a Goldilocks chair and more like a Goldilocks trap. The temperature is fine in theory. Everything else is hostile. Astronomers have a phrase for this newer view. They sometimes call it the abiogenesis zone instead of the habitable zone, the strip where life could start, in principle, ignoring all the other ways the universe tries to kill you. For now, Proxima b lives in a kind of scientific limbo, possibly habitable, probably hostile. The next chapter looks at the most direct threat of all, the steady wind of particles pouring out of the star, hour after hour, year after year. Our local star produces a quiet, constant breeze. A stream of charged particles, mostly hydrogen ions, drifts outward through the solar system at speeds of around 1 million miles per hour. This is the solar wind. It shapes the tails of comets, sculpts the boundary of our heliosphere, and shovels itself against the Earth's magnetic field every second of every day. Most of the time you never notice it. Our magnetic field deflects it. Our atmosphere absorbs what little gets through. The wind that pours off Proxima Centauri is something else entirely. Models suggest the stellar wind from Proxima can be hundreds to thousands of times stronger than the breeze from our own star, at a distance where any potentially habitable planet would sit. That is not a typo. Hundreds to thousands of times. Imagine standing in a gentle breeze on a calm afternoon, then being slammed by hurricane-force winds without warning. Now imagine that this is the calm setting, and the spikes are even worse. The wind matters for a single brutal reason. It strips atmospheres. When charged particles hit the top of a planet's air, they hand off energy to atmospheric molecules. Some of those molecules pick up enough speed to escape the planet's gravity and fly off into space. The process is called atmospheric escape. Over millions of years, a steady wind can chew away light gases like hydrogen and helium. Stronger winds can also dislodge heavier molecules like oxygen and water vapor. The atmosphere, slowly but relentlessly, leaks into the void. Earth resists this loss because of three things. Our planet is large enough to hold heavier gases by gravity. Our magnetic field channels most charged particles around us rather than through us. And our atmosphere is thick enough that the upper layers can absorb most of the abuse without exposing the lower layers. Take any of these protections away, and Earth slowly loses its air. It would not happen overnight. It would happen on the scale of hundreds of millions to billions of years. Around Proxima, the timescale shrinks dramatically. Scientists modeling the stellar environment of Proxima b have estimated that without a strong magnetic field, the planet could lose an Earth mass worth of atmosphere in less than a few 100 million years, possibly faster. That is geologically quick. By comparison, Earth has had life for over 3.5 billion years. If Proxima b lost its atmosphere in 200 million years, it would never have had time to develop the kind of complex biology that took our planet billions of years to evolve. Picture this in everyday terms. Imagine a swimming pool slowly being drained by a hidden leak. The water level falls inch by inch over the years. Now picture that same pool with a fire hose pointed at the bottom, blasting water out at high pressure. The pool empties in days. The difference between Earth's slow atmospheric leak and Proxima b's potential blowout is roughly that kind of ratio. There is one small hope. If Proxima b formed with vast amounts of water and gas, it might still have a thick atmosphere despite all the loss. The reservoir might be deep enough that there is still plenty left even after billions of years of stripping. We do not yet know. The James Webb Space Telescope and future ground-based giants will eventually look directly at Proxima b's atmosphere, if it has one. For now, the conclusion is grim, but hope dies hard. The next chapter starts asking the hardest question. How do we actually get there? Forget biology. Forget radiation. Forget the planet itself. Ignore everything except one single problem. To send a human spacecraft to Proxima Centauri in any reasonable amount of time, you need fuel. A lot of fuel. So much fuel that the laws of physics start to laugh at you. This is the fuel problem, and it is the wall that breaks almost every interstellar dream before it leaves the drawing board. Start with chemistry, the kind of fuel that powers every rocket humans have ever launched. Liquid hydrogen and liquid oxygen, or kerosene and oxygen, or the various solid propellants in rocket boosters. These reactions release energy in the range of a few megajoules per kilogram. They are extremely powerful by everyday standards and pitifully weak by interstellar standards. NASA has run the math on chemical rockets to Proxima. The result is absurd. NASA presented a quick scenario where we aimed to arrive at Proxima Centauri in 900 years with a conventional, chemical rocket without slowing down when we got there, which a real manned mission would certainly want to do. Using this method, there wouldn't be enough matter in the universe to fuel our rocket. Not enough matter in the universe. Stop and reread that. Big think. Even if you took every atom in every star in every galaxy and turned it into chemical rocket fuel, you could not push a chemical rocket to Proxima in less than 1,000 years. The exhaust velocity of chemistry is too low. To go faster, you have to throw mass out the back at higher and higher speeds, and chemistry caps out long before useful speeds are reached. This is the tyranny of the rocket equation. Adding more fuel does not help linearly. It helps less and less. Every extra kilogram of fuel you add also has to be carried, accelerated, and steered. which means you need even more fuel to move that extra kilogram. The math goes exponential the wrong way. Past a certain target speed, the rocket equation demands a fuel mass larger than the entire universe. Try a step up, nuclear thermal propulsion, where a small reactor heats hydrogen to enormous temperatures and shoots it out the back. NASA and DARPA are currently developing a prototype called DACO. A nuclear thermal rocket can roughly double the efficiency of a chemical rocket. A nuclear thermal rocket like DACO won't get us to Proxima Centauri, too little fuel, too short-lived a reactor, but it's a first step to applying nuclear fission, then fusion, to advanced propulsion. Doubling the efficiency moves the trip from absurd to merely impossible. So you keep climbing. Ion engines, solar electric propulsion, variable specific impulse magnetoplasma rockets. Each step gets a little better. Each step is still not enough to put humans at Proxima inside a single lifetime. The brutal truth is that every fuel humanity has ever burned, every battery, every reactor, every chemical reaction we have ever harnessed, simply does not pack enough punch per kilogram to do this job. We are trying to drive across an ocean in a car that runs on dry leaves. There are exotic options: antimatter, fusion, beamed laser power. Each one breaks through the fuel wall in a different way, and each one comes with its own brutal trade-offs. The next chapter starts with the most extreme answer of all, a fuel that is so powerful it could in theory get us to Proxima within a single human lifetime. If only we could afford to make a single gram of it. There is a substance that, when it touches normal matter, releases pure energy, not chemical energy, not nuclear energy, pure, complete conversion of mass into pulses of radiation at the maximum theoretical efficiency the universe allows. It is called antimatter. Every particle of normal matter has an antimatter counterpart. Electrons have positrons. Protons have antiprotons. Antimatter is identical in mass, but opposite in charge. When matter and antimatter meet, both vanish in a flash of energy. 1 gram of antimatter reacted with 1 gram of regular matter releases roughly the same energy as the Hiroshima bomb. A few kilograms, in principle, could push a spaceship to within a fraction of the speed of light. For interstellar travel, antimatter is the holy grail. A 2-stage antimatter rocket, according to one detailed analysis, could carry a probe to Proxima Centauri in about 40 years. 40 years! A grown person could leave Earth in their 20s and arrive at Proxima in their 60s. A real human mission to the nearest star, completed inside a single human life. The dream is right there on paper. Then you read the rest of the report. To make that 40-year journey, the rocket needs roughly 815,000 metric tons of antimatter fuel. 815,000 tons. Compare that to current human production. Humanity has made, in total, less than 20 nanograms of antimatter across every particle accelerator on Earth, across every research lab, across decades of work. The grand total is roughly the mass of a grain of pollen. The gap between 20 nanograms and 815,000 tons is, to use a polite word, enormous. To use a less polite word, it is impossible at our current level of civilization. The cost is even worse. Producing 1 gram of antimatter with current technology would require around 25 trillion kilowatt-hours of electrical energy. That is more energy than the entire world consumes in a year. The dollar cost is estimated to exceed $1 trillion per gram. Then multiply by 815,000 million grams. The number breaks every economic model ever built. There is also the small matter of storage. Antimatter cannot touch normal matter without exploding, so you have to suspend it in magnetic traps in perfect vacuum for years with no failures. A single bug, a single short circuit, a single mechanical jolt, and the entire ship vaporizes. Imagine fueling a car with nuclear bombs, and you are not far off. Despite all this, antimatter remains the gold standard against which every other propulsion idea is compared. It is the proof that physics permits a 40-year Proxima trip. The trip is allowed by the universe. It is just forbidden by economics and engineering. There is a softer alternative, not as fast, not as terrifying, but possibly within reach in our grandchildren's lifetime. A fuel that exists in trace amounts on the Moon, in larger amounts in the upper atmospheres of gas giants, and in essentially unlimited supply in the hearts of stars. That fuel is called helium-3, and it powers the dream of the fusion rocket. The next chapter looks at how a fusion drive could shrink the trip to Proxima to roughly 36 years, and why even this slightly more reasonable plan still slams into a wall of cost and engineering nobody yet knows how to climb. Inside every star burns the same engine. Hydrogen atoms, crushed together under immense pressure, fuse into helium and release staggering amounts of energy. That single process powers every star in the universe, including the one that warms your face on a summer afternoon. If humans could harness it cleanly, we could push spaceships faster than anything chemistry or nuclear fission can offer. The fusion rocket is the polished, almost reachable cousin of antimatter, not as ridiculous in mass, not as catastrophic in storage. Still very hard, but tantalizingly possible. The most studied design comes from a 1970s British project called Daedalus. A team of engineers spent years on paper working out a starship powered by fusion explosions, where tiny pellets of deuterium and helium-3 are zapped by electron beams and detonated inside a magnetic nozzle. The exhaust would scream out the back at a small fraction of the speed of light. The ship would accelerate slowly, then coast at roughly 12% of light speed. A modern Daedalus-style mission, aimed at Proxima Centauri, could reach the star in about 36 years. That is the magic number. If we could pull this massive undertaking off, a fusion rocket could reach our closest stellar neighbor in just 36 years, compared to the tens of thousands of years other methods would require. A baby born when the ship launches could grow up, finish school, get a job, marry, raise a family, and watch the first images of an alien world arrive when they are still middle-aged. For the first time in this entire conversation, a Proxima mission would fit inside a single human life. Now the price tag. The Daedalus design relied on fuel that, to put it gently, is hard to find on Earth. Deuterium is plentiful. Heavy water exists in the oceans. The hard part is helium-3. Unfortunately, the kind of fuel we would use, helium-3, is extremely rare on Earth. The project would cost about $5.267 trillion, and the study focused on unmanned missions. $5 trillion, a budget larger than the annual gross domestic product of every nation except a small handful. And that was for an unmanned probe. A crewed version would balloon the cost beyond any practical estimate. Where would the helium-3 come from? Two main candidates. The surface of the Moon, where billions of years of solar wind have deposited trace amounts in lunar soil, and the upper atmospheres of Jupiter and Saturn, where helium-3 exists in vast quantities and could in theory be scooped out by giant robotic harvesters. Both options would require infrastructure that does not exist. Lunar mining at industrial scale, atmospheric scooping at gas giants. Each project alone would be the most ambitious in human history. Then there is the engine itself. Inertial confinement fusion, the kind needed by Daedalus, has been chased by scientists for decades. In December 2022, a US laboratory finally achieved scientific break-even on a fusion experiment, meaning the energy output of a single shot slightly exceeded the laser energy hitting the fuel. The total power, however, was tiny, far below what a real engine would need. Going from a single break-even shot to a continuous Starship engine is roughly like going from a single match to a working volcano. Despite all of this, the fusion rocket remains the most respected serious proposal for crewed interstellar flight. Reachable physics, terrifying engineering, civilization-scale cost. There is one more route: build no engine at all, carry no fuel, Let the energy come from somewhere else entirely. The next chapter unfurls one of the strangest, most beautiful ideas ever drawn: the sail driven by lasers. For most of human history, sailors caught the wind. A breeze pushed canvas, canvas pulled ropes. The whole age of exploration ran on wind. So when engineers in the 20th century started looking for ways to power spaceships without carrying fuel, somebody asked an obvious question: what if you could catch light instead of air? That single question is the seed of the laser sail. Light is a strange thing. It has no mass, but it carries momentum. Every photon that hits a surface gives that surface a tiny push. The push is incredibly small. You cannot feel sunlight pressing on your skin. But across enormous surfaces, over enormous distances, those tiny pushes add up. Build a sail thin enough and wide enough, and a beam of light can accelerate it to extraordinary speeds. The most famous version of this idea is called Breakthrough Starshot, announced in 2016 by a team led by Russian billionaire Yuri Milner, with Stephen Hawking on the advisory board. The plan is bold and beautifully simple. Build a small fleet of tiny spacecraft, each weighing about 1 gram, each attached to a paper-thin sail roughly 4 meters across. Launch them into orbit, then fire a massive array of ground-based lasers at the sails. The lasers push the sails up to 20% of the speed of light in a matter of minutes. At 1/5 the speed of light, the trip to Proxima Centauri takes about 20 years. Think about that. A probe launched today could be sending back close-up images of an alien planet in 2046. The first generation of children who watched the launch could still be young enough to gather around a screen and see what no human eyes have ever seen. The physics is allowed. The engineering is brutal. The lasers alone would need to deliver around 100 gigawatts of power. That is roughly the output of 100 large nuclear power plants focused on a single sail for the entire boost phase. The array would have to be enormous, possibly covering a square kilometer of desert. The optics would need to track a target the size of a postage stamp at thousands of miles per second, with perfect precision, for the entire push. Then there is the sail itself. A paper-thin reflector facing a 100-gigawatt laser is being asked to bounce nearly all of that energy back without melting. Any imperfection becomes a focused absorption point. Any wobble translates to a deadly twist. The material must reflect over 99.9% of the incoming light, perfectly evenly for the entire boost. And there is no slowing down. The tiny probe blasts past Proxima at 20% of the speed of light and grabs whatever images and data it can in a flyby lasting hours. Then it sails into the dark forever. No orbit, no landing, no second chance. Even with all these limits, Breakthrough Starshot is the most realistic plan currently on the table. Scientists at major universities are actively designing prototype sails, prototype lasers, prototype electronics small enough to ride one. The dream is not science fiction. It is a budget problem and a materials problem. But this plan assumes a flyby. What about actually stopping when you arrive? That challenge sounds simple. It is not. The next chapter explains why slowing down at Proxima may be even harder than getting there. There is a saying in spaceflight: getting there is half the problem. The other half is stopping. For every interstellar plan, this is the moment the romance dies. You can fire a rocket forward. You can ride a laser beam. You can fold antimatter into a magnetic bottle and let it explode out the back. All of these accelerate you. None of them, by themselves, slow you down at the other end. The math of slowing down is a punishing mirror image of the math of speeding up. If a fusion rocket needs 10 years to accelerate to 12% of light speed, it needs another 10 years to break to zero. That doubles the trip. It also doubles the fuel, and in the rocket equation, doubling the fuel is not doubling the cost. It is squaring the cost, sometimes worse. For Breakthrough Starshot, the problem is fatal. Those 1-gram sails have no engines, no fuel, no way to slow down. They are not arriving at Proxima Centauri, they are stampeding past it. A flyby at 20% the speed of light means the probe spends less than a minute within useful imaging range of Proxima b, less than the time it takes to brush your teeth. Whatever pictures it grabs, whatever measurements it streams, are gathered in a blink. Some scientists have proposed clever ideas. One concept uses the gravity of Alpha Centauri A and B, the brighter pair of stars near Proxima, to bend a probe's path and slow it down enough to settle into orbit. This is called the photogravitational assist. The math works in theory, but it requires a passing speed far slower than 20% of light, and it depends on the sail being able to swivel and reflect light from the new stars to apply a braking force. Another idea uses a second sail back home. The mother sail accelerates the daughter sail, then catches reflected light from the daughter to brake itself at the destination. Beautiful on paper. Engineering nightmare in practice. For larger missions like a crewed fusion ship, there is no clever trick. The ship simply has to carry its own brakes, half the fuel for acceleration, half for deceleration. The trip becomes longer, heavier, more expensive. 40 years stretches to 60, 60 stretches to 80. The window of a human life closes again. There is a deeper irony hidden in all of this. Stopping at Proxima Centauri is harder than going there because Proxima itself offers very little help. Our local star uses its gravity and its solar wind to slow down arriving comets and asteroids over millions of years. But a ship traveling at relativistic speeds blows past Proxima's gravity well so quickly that the star barely has time to tug at it. The very thing that makes interstellar travel possible, going incredibly fast, makes arrival incredibly difficult. To picture it, imagine driving down a highway at 500 miles per hour and trying to pull into a parking spot. You will overshoot the parking lot, the town, and the entire state. Slowing down from interstellar speeds is exactly the same problem, only stretched across light years. So, a one-way flyby is possible. A real visit is not, at least not with anything we know how to build today. And every year spent traveling, whether one way or two, exposes the crew, the electronics, and the ship to the deep space environment. Cold, dark, empty, or so it looks. The next chapter shows what is actually waiting in that empty space, and why interstellar travelers may be killed slowly by something they cannot see. Outer space looks empty. Most of it is. Between stars, between galaxies, between everything there is mostly nothing. A few atoms per cubic centimeter on average. Less air in 1,000,000 miles of space than you exhale in a single breath. But space is not actually empty. It is filled with something else. Radiation. Every direction you look, in deep interstellar space, high-energy particles are streaking through the vacuum. These are called cosmic rays. They come from supernovas, from black hole jets, from active galactic nuclei millions of light years away. They have been traveling for thousands or even millions of years before reaching the inside of an interstellar spaceship. And when they hit human tissue, they tear DNA apart at the molecular level. On Earth, you are mostly safe from cosmic rays. The atmosphere absorbs them. The magnetic field deflects them. By the time any of those particles reach the ground, most have been smashed into harmless secondary showers. Astronauts in low Earth orbit get more exposure, but the planet's magnetic field still shields them from the worst of it. Astronauts who fly to the moon, like the Apollo crews, started feeling the real impact. They reported seeing flashes of light inside their closed eyes, caused by high-energy particles passing through their eyeballs. Now imagine spending 40 years in deep space, far from any planet, far from any star, in the open dark where cosmic rays arrive from every direction at full intensity. Estimates suggest that on a 3-year round trip to Mars, an astronaut would receive a lifetime allowable radiation dose at least 3 times over. On a 40-year Proxima trip, the dose is roughly 10 times worse. Cancer rates climb. Cognitive decline appears within months on long missions. Sleep cycles break. White blood cell counts drop. Cataracts form. There is also another problem. Galactic cosmic rays come in flavors that include heavy ions, like iron nuclei, accelerated to nearly the speed of light. When one of these heavy ions punches through a human body, it leaves a track of dead cells, dozens or hundreds of cells wide. Repeated impacts can produce damage that the body cannot repair. Brain cells, which do not regenerate, accumulate hits permanently. Some animal studies on Earth, using particle beams to mimic cosmic rays, have shown lasting cognitive impairment after relatively modest doses. Shielding is hard. The heaviest shielding materials, lead and tungsten, are too dense to carry in useful amounts. The lightest, like water and polyethylene, work surprisingly well per pound, but require thick walls. Some plans propose surrounding a spaceship's crew compartment with massive tanks of water that serve double duty as radiation shield and life support reservoir. Others suggest spinning the ship inside a magnetic bubble that mimics Earth's protective field on a small scale. None of these solutions have been built at full scale. There is one final twist. As a ship accelerates to a meaningful fraction of light speed, ordinary hydrogen atoms in interstellar space start to look like radiation. From the ship's frame of reference, those slow background atoms become high-energy particles slamming into the front of the hull at relativistic speeds. The faster you go, the more deadly the background becomes. So speed costs lives. And the next chapter looks at one of the most underestimated dangers of interstellar travel, the simple problem of running into something at a quarter the speed of light. A grain of sand is harmless. You step on grains of sand at the beach without thinking. The wind blows them past you all the time. You can hold 1,000,000 grains of sand in your 2-cupped hands and weigh almost nothing. Now accelerate 1 grain to 1/4 the speed of light, and that single grain becomes a bomb. This is the small, almost forgotten danger that hides in every plan to fly between the stars. Interstellar space contains a thin haze of dust, tiny grains of carbon, silicate minerals, frozen water, scattered widely but absolutely everywhere. The density is incredibly low. On average, only a handful of dust grains per square kilometer of any given cross-section of space. But across a journey of trillions of miles, your ship is sweeping out a column of space, billions of cubic miles in volume. Sooner or later, you hit something. A dust grain weighing 1/1,000,000th of a gram, slamming into a spaceship at 20% of the speed of light, releases roughly the energy of a hand grenade detonating against the hull. A grain weighing 100th of a gram delivers something closer to a stick of dynamite. Every encounter punches a crater into the leading edge of the ship. After enough encounters, the front of the ship is shredded. NASA estimates from the Space Shuttle program offer a sobering reference. If we travel anywhere through space at significant fractions of the speed of light, almost certainly a requirement for interstellar travel, then impacting interstellar dust, or larger objects like space debris or micrometeoroids, could be disastrous. Even in the short trips we made during the Space Shuttle program, more than 100 shuttle windows were replaced after being chipped or cracked by space debris. And the shuttle was crawling, in cosmic terms. Interstellar speeds make those impacts hundreds of millions of times more energetic per particle. Big think. Designers of breakthrough Starshot have already accepted that some of their tiny probes will be destroyed in flight. Their plan is to launch a swarm of hundreds or thousands of probes and accept that perhaps only a fraction will arrive intact. That makes sense for 1-gram chips. It does not work for a crewed ship. A human spaceship needs armor. Real armor, thick, heavy, sacrificial. The most studied approach is something called a Whipple shield, a thin outer wall a few feet ahead of a thicker inner wall. When a particle hits the outer wall, it vaporizes both the wall and itself into a spray of plasma. The plasma then splatters across the inner wall over a wider area, spreading the impact and reducing the chance of a clean puncture. Modern probes use Whipple shields against centimeter-scale debris in low Earth orbit, Scaling them up to handle interstellar grains at relativistic speeds is uncharted territory. There is also no way to dodge. At 20% of the speed of light, by the time you spot a grain of sand a few thousand miles ahead, you have less than a millisecond to react. You cannot move the ship out of the way. You cannot vaporize the grain in flight because every shot would require a laser too powerful to carry, aimed too precisely to control. So the dust storm continues. Hit after hit, the ship slowly gets battered until the cumulative damage starts to compromise structural integrity. Even if the ship survives, the people inside must somehow live through the entire trip. The next chapter looks at the most ambitious idea ever proposed for that problem, the generation ship. Stop thinking about getting to Proxima fast. Imagine going there slow, very slow. So slow that nobody who launches will ever arrive. Slow enough that great-grandchildren of the original crew are the ones who finally see the new world. This is the generation ship, and it might be the only honest plan we have. The idea is brutally simple. Build a self-contained world, a vast hull miles long, spinning to create artificial gravity. Inside, farms, forests, apartments, schools, a small city sealed against the void, fully recycling air, water, and waste. A few hundred to a few thousand humans live their entire lives inside this ship. They marry, they have children, they die. Their grandchildren grow old, generations pass, the ship coasts through the dark, century after century, until one day a faraway descendant looks out a window and sees a red star looming ahead. At current human propulsion levels, around 0.067% of the speed of light, this kind of ship would need around 6,300 years to reach Proxima. That is roughly 250 human generations. Proxima Centauri is 4.2 light-years from Earth, a distance that would take about 6,300 years to travel using current technology. Such a trip would take many generations. 250. MIT Technology Review. To grasp that number, run history backward. 250 generations ago, the Great Pyramids of Egypt had not yet been built. The wheel was a recent invention. Humans were still figuring out the basics of metalwork. The civilization that finally arrives at Proxima would be as distant from the civilization that launched as we are from the people who carved the first cuneiform tablets. Now imagine the people who actually live on this ship. The first generation knows Earth. They remember oceans, weather, sunsets, the sight of an open sky. They volunteered. They chose this life. Their children grow up inside a metal world. The walls are real. The ground is metal. The closest thing to a horizon is a long, curving floor that climbs up into the ceiling. They have never seen the open sea. They have never felt the wind that did not come from a vent. They believe in Earth the way modern children believe in the moon, as a real place they have only seen in pictures. By the 10th generation, Earth is a legend. By the 50th, half the crew may not believe Earth exists at all. The original mission may be lost. The original goal may be forgotten. The ship has become a country, an entire civilization, with its own myths and politics and religions. The leaders of the moment may decide they like coasting through space. They may decide they want to turn around. They may decide to attack the children of the families who built the engines. This is not a movie plot. This is the actual problem written about by serious researchers. A ship civilization carrying 250 generations is a long, slow social experiment, and no experiment of that length has ever been tried. There is one more practical concern that makes the dream even more fragile. Genetics. A small population breeding within itself for thousands of years eventually faces inbreeding problems. The next chapter looks at the math of how many humans you would actually have to send just to make sure someone arrives alive on the other end. If you were going to send a generation ship to Proxima Centauri, how many people would you put on board? The instinct says a handful, 2 pairs of adults, maybe a dozen. The cost of every extra person is enormous. Every extra body needs food, water, air, space, life support, and a slice of the ship's recycling capacity. Smaller is cheaper. The trouble is, smaller dies. A research team in France ran the math in detail in 2018, using a simulation that tracked genetic diversity across many generations. Their starting question was specific. What is the smallest crew that can leave Earth and arrive at Proxima with a population still healthy enough to colonize a new world? They considered initial group size, age distribution, life expectancy, infertility rates, and the probability of accidents. Their answer was sobering. Since it would take at least 6,300 years to reach the closest star to our Sun, enough men and women to produce many genetically healthy generations would need to make the trip. A study by Frederick Marin and Camille Bellufi suggested that a minimum healthy founding population of around 98 unrelated adults would be needed for a 6,300-year voyage with current technology. Below that number, inbreeding catches up, and the line either fizzles out or arrives so genetically damaged that any colony would collapse within a few generations. MIT Technology Review: 98 adults, not as many as people often picture, but far from a couple of romantic pioneers. And that is the absolute flaw, the lower edge of survival. A real mission would want a margin of safety, several hundred adults, possibly thousands, each, one with carefully managed reproduction over the centuries to maintain genetic diversity. Each one with a job, a place, a future, a role. Other studies have pushed the number higher. Some demographic models suggest a starting population of around 40,000 may be needed if you want the crew civilization to remain technologically capable over 6,000 years, with enough specialists in every craft to maintain the ship and pass on the knowledge. 40,000 adults is not a crew. It is a small city in a metal hull, coasting through the dark, for 60 centuries. Then there is the dating problem. Real humans do not pair off by genetic optimization spreadsheets. They fall in love, they feud, they form cliques, they reject the matches suggested by the central computer. A generation ship has to manage all of this without becoming a tyranny and without falling into chaos. Some designs propose frozen embryos as a backup. Thousands of carefully selected sperm and egg combinations kept in cryogenic storage, used to refresh the gene pool every few generations. This delays the inbreeding problem, but introduces new ones. Who decides which combinations get thawed? Who raises the resulting children? What happens if the embryos turn out to be damaged after centuries in storage? There are no clean answers. Every approach trades one risk for another, and we have not yet talked about the worst risk of all: not death, not radiation, not collision. Something quieter, something that has destroyed groups of humans many times in history, even on Earth, even surrounded by everything they needed. The next chapter walks into the psychological black hole that may be the real killer of any generation ship. In 1983, 6 volunteers entered a sealed underground bunker in Italy for a study of long-term isolation. They lived without clocks, without contact with the outside world, with constant low light and no day-night cycle. Within weeks, their sleep schedules drifted. Within months, several became withdrawn, paranoid, and emotionally unstable. The experiment was eventually cut short. That study lasted a few months. A generation ship to Proxima Centauri lasts 6,000 years. The psychological toll of long-duration space travel is one of the most underestimated problems in interstellar planning. Engineers love hardware. They love numbers. They love thrust and shielding and fuel mass ratios. They are less comfortable with the soft, slow rot of human minds in confined spaces. Russian and American space agencies have run analog experiments for decades. Mars 500, a 520-day simulated Mars mission in Moscow, ended with crew members exhibiting depression, sleep disruption, and conflict. Several of the participants did almost nothing productive in the final months. They simply went through the motions, locked in a kind of emotional fog. Now scale that up. 520 days is around 1.5 years. A Proxima generation ship covers thousands of years, with people who never had a choice in the first place. They were born on the ship. They will die on the ship. Their entire universe is a hull. Several specific dangers haunt long voyages. The first is sensory deprivation. Outside the windows there is no movement. The stars are too far to change visibly. The dark is constant. Day after year after century, the view never updates. The human brain, evolved for landscapes that change every minute, eventually struggles. The second is social compression. A few hundred or a few thousand people sharing the same hallways, the same dining halls, the same recycled air for entire lifetimes. There is no escape. You cannot move out. You cannot quit your relationship and run to another town. Every interaction echoes for years. Grudges become epic. Mistakes are never forgiven. Communities can fracture along family lines, religious lines, even who knows who. The third is meaning. Humans are not engineered for purposeless existence. They need stories, goals. On a multi-millennium voyage, the original goal of reaching Proxima may feel less and less real to the people in the middle generations. They did not choose the mission. They did not see the launch. They will not see the arrival. They are simply passing along genes and supplies. The temptation to give up, to coast, to simply exist, must be constant. The fourth is rebellion. Eventually, some generation will decide they would rather turn the ship around, or stop it, or aim it somewhere else. There is no guarantee that the people in charge after 1,000 years will share the values of the people who launched. Some plans address these dangers with extensive psychological screening, mandatory therapy, elaborate cultural rituals, even genetic preselection for stable personalities. None of these have been tested over 1,000 years. None can be. There is also the body to consider. The mind may rot in confined spaces, but the body has its own slow collapse on long voyages, even without isolation, even with everything you need. The next chapter explains what happens to bones, muscles, and organs over decades in deep space. Spaceflight breaks the human body. This is not a theory. It is documented in every long-duration astronaut who has come home from the International Space Station. The most obvious damage is bone loss. In microgravity, the skeleton stops being asked to support body weight. Bone cells, sensing no load, start dissolving the very bones they live in. Over 6 months in orbit, astronauts lose roughly 1 to 2% of their bone density per month, especially in the hips, spine and legs. After a year, the loss can exceed 15% in load-bearing bones. Recovery on Earth is slow, sometimes incomplete. Muscle loss is even faster. Without gravity to fight against, muscles atrophy at a stunning rate. Astronauts on the International Space Station spend more than 2 hours a day exercising on specially designed machines just to slow the damage. Even with this brutal routine, they return to Earth weaker than they left. Walking is hard. Standing is hard. Some need wheelchairs in the first days back. The heart shrinks too. In microgravity, the heart no longer has to pump blood against gravity from the legs back up to the head. The fluid distribution in the body changes. Blood pools in the upper chest and face. The heart, sensing reduced demand, becomes a smaller, weaker muscle. Astronauts return with measurable changes to cardiac structure. The eyes are perhaps the strangest casualty. Long-duration astronauts often return with vision problems caused by changes in pressure inside the skull. The condition is called spaceflight-associated neuroocular syndrome. Some astronauts need new glasses after a 6-month mission. After a multi-decade trip to Proxima, the cumulative damage to eyesight is unknown. There is also immune system suppression. Microgravity changes how white blood cells function. Latent viruses, like herpes and chickenpox, can reactivate in space. Even in astronauts who have not had a flare-up in decades, wounds heal more slowly, inflammation patterns shift, cancer risk rises due to radiation. All of this is for astronauts on 6-month rotations. Multiply by 80, by 800, by 6,000 years of generation ship. There are partial solutions. Spinning the ship to create artificial gravity is one of the most studied. A rotating cylinder, like the ones imagined in science fiction, would push everything inside outward against the floor. The effect mimics gravity for the body. It also creates strange side effects. Stand up too fast, and the spin throws you sideways. Walk against the rotation, and you feel lighter. Walk with it, and you feel heavier. Inner ears protest. Some people get permanently nauseous. The size matters. A spinning ring needs to be at least a few hundred feet in diameter to feel comfortable. Smaller rings have to spin too fast, and the differential between head and feet becomes uncomfortable. Building a structure that large, in space, light enough to be accelerated to interstellar speeds, is at the edge of what humans know how to engineer. There is also the problem of children. Almost everything we know about human bone, muscle, and brain development assumes growing up in Earth gravity. Children born and raised in even artificial gravity, slightly different from Earth's, may end up with subtly different bodies, different bone structure, different brain wiring. After 100 generations, the people who land at Proxima may not be quite the same species that left, and while they fly, they cannot really talk to home. The next chapter explores what it means to send a message across years of empty space. Imagine telling your mother you love her and waiting 8 years for the reply. That is the communication reality of an interstellar mission. Radio waves travel at the speed of light. Light takes more than 4 years to cover the distance between Earth and Proxima Centauri, so any message from a Proxima-bound ship takes years to arrive home, and the response takes the same years to come back. A single hello and how are you exchange spans roughly 8.5 years. This kills the entire concept of mission control as we know it. On Earth, when something goes wrong on the International Space Station, ground crews in Houston and Moscow respond within seconds. They watch live video, talk to astronauts in real time, run simulations in parallel, and uplink fixes within minutes. The whole point of having a ground team is rapid response. On a Proxima ship, ground control becomes useless. By the time a problem is reported, half a decade has passed. By the time advice arrives back at the ship, another half-decade is gone. Whatever caused the problem either killed everyone long ago or was solved by the crew themselves, with no help from Earth. So the ship must be self-sufficient. Every doctor, every engineer, every mechanic, every farmer must be on board. Every spare part must be carried or manufactured on the way. Every emergency must be solved by the people present. Earth becomes a distant ancestor, helpful in legacy but irrelevant in practice. Cultural drift compounds the problem. 8 years of round-trip delay means conversations cannot really happen. Letters, perhaps. Recorded messages from grandparents, played back to grandchildren who never met them. By the 3rd or 4th generation on the ship, contact with Earth feels less like communication and more like reading old books. The languages may drift. Slang appears on Earth that the ship never hears. Slang appears on the ship that Earth never hears. The two cultures separate. If the ship somehow reaches Proxima and a colony forms, the situation gets stranger. A radio message from the colony arrives at Earth around 4 years after sending. By the time Earth replies, another 4 years have passed. Decisions on the colony are made entirely without input from home. A pandemic on the colony plays out in full before Earth even knows it started. There is no way to fix this. The speed of light is the absolute legal limit. No faster-than-light communication exists outside the boundaries of speculative physics. Quantum entanglement, often misunderstood in pop science, cannot be used to send information faster than light. Wormholes remain theoretical. Tachyons remain unconfirmed. The practical result is that humans living at Proxima will be the most isolated population in human history by orders of magnitude. Imagine the loneliest village in Siberia, then multiply that loneliness by 10,000. There is no road, there is no flight, there is no emergency rescue. If the colony fails, Earth finds out years later, and there is nothing anyone can do. It is a strange kind of cosmic distance, the kind measured in lost conversations. Every word spent on a Proxima mission spends years getting where it is going. Every silence on the other end means nothing yet. Maybe something happened. Maybe it just has not arrived. The whole reason for going is to find something worth the trip. The next chapter asks a hard question. What if Proxima b is already dead? After everything, after the lasers and the sails and the bone loss and the generations and the silence, you arrive. The ship slows, the engines cool, a small probe peels off the main hull, dives toward the rocky planet, and begins its scans. What does it find? Possibly nothing. The most uncomfortable possibility about Proxima Centauri b is that it may already be a corpse. Not a dying world, not a struggling one. A world that died billions of years ago, before life had a real chance to gain a foothold. Proxima is older than our own local star. Estimates put its age somewhere between 4.5 and 7 billion years, possibly older. Across that span of time, the flares, the stripping, the radiation could have already ended any chemistry that ever started. What would such a dead Proxima b look like up close? Most likely, a sterile, rocky surface, cratered, dry, possibly cracked. The day side would be warm, baked by infrared light from the red dwarf, but with no greenhouse gases left to trap heat efficiently. The night side would be deeply cold. The terminator zone, the thin ring of permanent twilight, might still have some lingering ice or frozen volatiles, possibly evidence of an ancient ocean, long since boiled and blown away into space. Imagine landing a probe on that surface. Cameras swing around. The horizon is short, much shorter than on Earth, because the planet is smaller in radius. The red star hangs huge and motionless in the sky. The ground is sand and rock. No clouds, no wind, no biology anywhere, ever. There is something deeply melancholy about this picture. We will have spent the equivalent of millennia of human civilization, the wealth of nations, the lives of dozens of generations, to find a tombstone of a world, a planet that briefly might have been like Earth before the universe stripped it down and left a husk. Even worse, this might be the typical result for red dwarf planets. There are roughly 200 billion red dwarf stars in our galaxy. They are the most common type. If most of them have flare-stripped, atmosphere-deprived dead worlds in their habitable zones, then the galaxy is full of failed Earths, worlds that almost made it, worlds that started toward biology but never finished. This is one of the proposed solutions to the Fermi paradox, the question of why we have not detected any other technological civilizations in the galaxy. Maybe complex life is extremely rare because most planets in habitable zones around the most common stars get killed by stellar activity early. Maybe Earth, with its quiet, calm yellow neighbor, is a lucky exception rather than a typical case. There is still hope. Proxima b might have an atmosphere we have not yet detected. It might be lucky in some way we have not modeled. Future telescopes may directly image the planet and tell us what is really there. The James Webb Space Telescope, the extremely large telescope being built in Chile, and the upcoming Habitable Worlds Observatory are all designed to take this kind of look. If the answer is barren, the news will be world-changing in a quiet, devastating way, because Proxima b is the closest possible new home. If even the nearest planet to Earth is dead, the next nearest worlds are even harder to reach. The next chapter looks at the small triangle of stars that surrounds Proxima and the slightly better neighbors hiding just behind it. Proxima Centauri is not alone. It is part of a triple star system. The other two stars, Alpha Centauri A and Alpha Centauri B, are much brighter, much larger, and much more familiar in size and color than the dim red Proxima. To the naked eye, Alpha Centauri A and B appear as a single bright point in the southern sky. They are the closest Sun-like stars to Earth. The catch is that they are slightly farther than Proxima, about 4.37 light-years, a bit beyond their tiny red sibling, and they orbit each other tightly, swinging around their common center of mass over a span of about 80 years. Proxima itself, the smaller, dimmer companion, is loosely tied to the pair on an enormous 550,000-year orbit. For interstellar planning, this matters a lot. Alpha Centauri A is a star very similar to our own. Same yellow color, slightly larger, slightly brighter. Alpha Centauri B is a smaller orange star. Both are calm, both are stable, both lack the violent flaring that plagues Proxima. If a habitable planet exists around either of those stars, it would have a much better chance of holding onto its atmosphere and producing real durable life. The frustrating thing is that, for decades, astronomers searched these stars hard and found no clear planet. Detection methods favored short-period planets close in, and the binary nature of the system made data noisy. Then, in 2022, a candidate planet around Alpha Centauri A was tentatively reported, with a possible orbit roughly inside the star's habitable zone. The detection remains unconfirmed. New observations are ongoing. If a planet exists around Alpha Centauri A, in the right orbit, it would be one of the most exciting targets in the entire universe. Imagine a planet orbiting a star almost identical to our own, at a distance that allows liquid water, free of the brutal flares of red dwarfs. The kind of world where actual Earth-like biology could plausibly arise and persist. It would also still be 4.37 light-years away, not closer to home in any meaningful sense. The same propulsion problems, the same radiation, the same generation ship math. Just a slightly more inviting destination, at the same brutal distance. There is one more odd twist. From any planet orbiting Alpha Centauri A, the other star, Alpha Centauri B, would appear as a bright orange object in the sky, far brighter than our own moon, but not as bright as our own local star. It would orbit the planet's sky over decades, sometimes near, sometimes far. And Proxima would be a faint red dot somewhere in the distance, barely visible. So the closest small system to Earth is not a single dim red dwarf. It is a small family of stars. One angry red dwarf with at least one planet, possibly dead. Two calmer sun-like stars, possibly with planets of their own, much more promising for life. This changes the way humans should think about interstellar exploration. The first stop is not necessarily the most attractive. Proxima is closest, but Alpha Centauri A and B may be the real prize. A mission to the system as a whole with the flexibility to study all three stars could fundamentally rewrite what we know about life in the galaxy. But it is not just our local neighbors that move. The next chapter looks at another star, currently farther away but heading towards us at terrifying speed. Stars are not fixed, they move. The night sky we see today is not the same night sky our ancestors saw, and not the same one our descendants will see. The constellations slowly drift apart, dragged by the random motions of stars orbiting the galactic center. Most of the changes are too slow to notice in a human lifetime. A few are surprisingly fast. One of those fast-moving stars is called Barnard's star. Right now, Barnard's star sits about 6 light-years from Earth. That makes it the fourth closest star system to our own after Alpha Centauri A, B, and Proxima. It is a small red dwarf, even smaller and dimmer than Proxima, and it is moving across our sky faster than any other known star, an apparent motion of around 10 arcseconds per year. That sounds tiny. In astronomical terms, it is screaming. The reason is direction. Barnard's star is coming almost straight toward us. It will not hit us. but it will get a lot closer. Astronomers have calculated that in roughly 9,700 years, Barnard's star will reach its closest approach to Earth at a distance of about 3.8 light-years. Barnard's star is approaching the Sun so rapidly that around 11,700 AD, it will be 3.8 light-years from the Sun, and thus the closest star to our own. Garcia Sanchez et al. 2001. At that point, Barnard's star will officially become the new nearest star to Earth, replacing Proxima Centauri. The crown of nearest stellar neighbor will pass to a different red dwarf. 3.8 light-years is closer than Proxima today, but it is not closer enough to matter for human travel. A Parker Solar Probe-style ship would still need over 6,000 years to reach Barnard's star at that point. A fusion rocket would still need decades. The improvement is real, but it does not crack open the door to easy travel. Even more interesting things may happen at much longer timescales, roughly every million years or so. On average, some random star passes within a few light-years of our local star. These are called stellar flybys. Most are unremarkable. A handful over the lifetime of our solar system may have come close enough to disturb the cloud of comets that surrounds us, sending icy bodies tumbling inward toward the inner planets. One of the most famous predictions involves a small star called Gliese 710. Astronomers estimate that in around 1.3 million years, Gliese 710 will pass through the outer edge of our cometary cloud, possibly causing a slow shower of comets to drift toward the inner planets over hundreds of thousands of years. Some researchers have proposed this kind of disturbance as a possible cause of mass extinctions on Earth in the distant past. The bigger lesson is simple. Distance to the nearest star is not a fixed property of the universe. It is a temporary, slowly changing number. Right now, Proxima holds the title. In 10,000 years, Barnard's star will hold it. In 1,000,000 years, somebody else. But the changes are slow. None of them cross the wall that separates interstellar dreams from human capability. The next chapter looks at one more thing the universe does to make the dream even crueler: the way time itself bends when you try to push too fast. Albert Einstein, in 1905, introduced a strange idea. Time is not a fixed background. It bends. The faster you move relative to someone else, the slower your clock ticks compared to theirs. At everyday speeds, the effect is microscopic. At the speeds of jet airplanes, atomic clocks can measure it. At the speeds needed for interstellar travel, time dilation becomes a major character in the story. For a Proxima mission, time dilation is both a gift and a curse. Imagine a ship that accelerates to 90% of the speed of light, coasts for a while, and decelerates at the other end. The trip to Proxima Centauri, measured by an Earth-based clock, takes a little over 4.7 years. Measured by the ship's clock, it takes about 2 years. The crew experiences only 2 years of life. The Earth that watches the trip from outside has experienced more than 4. Push the speed higher. At 99% of the speed of light, the ship's clock experiences only about half a year for the same trip. At 99.9%, less than 2 months. At ridiculous fractions of light speed, an entire interstellar journey could happen, from the crew's point of view, in a few weeks. This is the gift. From inside the ship, time dilation makes long distances feel short. A crew flying at near light speed could, in principle, cross the entire galaxy in a single working lifetime, as long as they had enough fuel to keep accelerating. The curse, of course, is what happens on Earth. While the crew is experiencing weeks or months, Earth is experiencing years, decades, centuries. The home they left ages. Friends die, children grow up, and have grandchildren. By the time the ship returns, the people who waved at the launch are long gone. The civilization that sent the mission has changed beyond recognition. The crew steps off the ship into a future they were never invited to. This is sometimes called the twin paradox. One twin goes on a near light speed trip. The other stays home. When the traveling twin returns, the homebody twin has aged far more. They might be standing at the gravesite of their own brother or sister. For a Proxima mission, the math is brutal, but not as extreme as some science fiction implies. Even at 90% of light speed, the ship's crew ages about half as fast as Earth. A round trip lasts roughly 5 years for them, 10 for Earth. Survivable, strange, permanent. And reaching 90% of light speed is a fantasy. We do not have engines, fuels, or shielding that can carry a crew to anywhere near that speed. The honest, realistic upper limits, with fusion or beamed power, sit somewhere in the range of 10 to 20% of light speed. At those speeds, time dilation is real but modest. The Earth-ship clock difference for a Proxima trip becomes a few months at most, not enough to dramatically save the crew, not enough to dodge the years of effort. So Einstein's gift sits there, taunting us. The universe will let humans travel almost anywhere in subjectively short times if only they can reach near-light speeds. But near-light speeds are exactly what our technology cannot deliver. The door is unlocked. The doorknob is too high to reach. The next chapter steps back and asks the biggest question of all. What if distance, by itself, is the reason the galaxy looks empty? In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos. The conversation drifted to the possibility of alien civilizations and faster-than-light travel. Fermi listened for a while, then asked a simple question. Where is everybody? That question became the Fermi paradox. The galaxy is incredibly old. Our local star formed about 4.5 billion years ago, but many stars in the Milky Way are far older. If even a fraction of those older stars produced civilizations, even slow-moving ones, those civilizations should have had millions of years to spread across the galaxy. The Milky Way should be busy. Probes, signals, lights, something. Instead, the sky is silent. No clear signals, no alien probes in our solar system, no obvious megastructures around nearby stars. We listen with radio telescopes and hear nothing. We watch with optical telescopes and see nothing built by anyone but us. There are many proposed solutions to the Fermi paradox: the Great Filter, the zoo hypothesis, the dark forest. Each is its own essay. But after everything you have just learned about the journey to Proxima Centauri, one of the simplest possible answers may now feel obvious. Maybe distance is the great filter. Maybe interstellar travel is simply too hard for almost any biological species, anywhere. Maybe physics permits it in theory but forbids it in practice. Because of the fuel problem, the radiation problem, the dust problem, the generation problem, the psychological problem, the genetic problem, and every other problem stacked on top of each other. Maybe civilizations rise on their own planets, build their own technology, listen to their own radios, and then stay home, not because they choose to, because they cannot leave. If that is true, the silence of the galaxy is not surprising. It is the only possible result. Every species that reaches our level of technology hits the same wall we are hitting now. Some give up. Some keep trying for centuries, then run out of resources. A few send a handful of slow probes that arrive at neighboring stars after their home civilization has already collapsed. The probes find nothing alive. They send back a few signals. They die. This explanation has a strange comfort to it. It does not require any extra mystery. It does not require a galactic conspiracy of hidden aliens. It does not require everyone to be dead. It only requires the universe to be exactly as big as it is, and biology to be exactly as fragile as it is, both of which are clearly true. The Proxima problem is, in this view, the universal problem. It is the first wall every species hits. Some break through, most do not. Maybe the silence of the sky is the sound of countless intelligent beings, each looking up at their own night sky and asking themselves the same question. Why is it so far? Why is it so empty? It is also possible that the wall can be crossed, that somewhere out there, an older civilization figured it out, built engines we have not imagined, and currently lives among the stars. We just have no evidence yet. For now, we sit on a single rock in a small system around a calm yellow star with one closer red ember hanging in the southern sky, 4.25 light-years away, and the distance between us and that ember is, for all practical purposes, the distance to forever. The next chapter steps back and looks at the absurd shape of human ambition compared to the universe we live in. For a moment, set aside the science, set aside the math, set aside the propulsion and the radiation and the bone loss. Look at the bigger picture of what humans have ever done. The longest continuous engineering project in our history is the Great Wall of China. Across roughly 2,000 years, generations of laborers added sections to it. The total length, with all branches included, is around 13,000 miles. Today, large parts of it have collapsed. Even the wall, the most ambitious cooperative construction project in human civilization, did not survive intact for the length of time a Proxima generation ship would need to remain functional. The longest documented continuous human institution is probably some of the oldest religious traditions, with chains of texts and ceremonies stretching back roughly 5,000 years. A generation ship would have to maintain functioning leadership, infrastructure, and culture across a span longer than that, without backup, without resupply, without ever being able to walk outside. Look at it another way. The combined budget of every human space program ever flown, including all NASA missions, all Russian and Soviet missions, all European and Japanese and Chinese and Indian and private launches, totals to roughly $1 trillion across the past 70 years. A Daedalus-style fusion mission to Proxima alone was estimated at over $5 trillion in unmanned form. That single mission alone would cost more than every space program in human history combined by a factor of 5, and it would deliver no crew. For a crewed mission, the numbers spiral. Hundreds of trillions of dollars, decades of dedicated industrial capacity, a coordinated multi-century effort by an entire planetary civilization. Cooperation on a level humans have never managed for any other project. Wars and economic crashes and political turnover would have to leave the mission untouched for decade after decade. Our species has trouble keeping highway bridges in good repair for 50 years. We are talking about engineering on the scale of millennia. This is not a reason to give up. It is a reason to be honest about the size of the problem, because giving up is also a kind of failure. The lesson of human history is that ambitions that look impossible at first sometimes become routine over centuries. Flying machines, heart transplants, pocket computers, the moon, none of these were obvious. All of them were once dismissed as fantasies. It is also possible that the path to the stars does not look like the path science fiction predicted. It may not be giant ships and dramatic launches. It may be tiny probes sent over centuries, one after the other, slowly building up data. It may be sending machines first, and people much later, possibly much later. It may be uploading minds into hardware that can survive the trip in ways biology cannot. Or it may be never. Some problems do not have solutions. Some doors do not open. The universe is allowed to be larger than human ambition, and there is no rule that says we must be able to cross it. What we can do, right now, is keep looking. Telescopes get better every year. The James Webb Space Telescope has already begun to study the atmospheres of distant exoplanets. The extremely large telescope, being built in Chile, will eventually be able to take real images of nearby Earth-sized worlds. Even if we cannot go, we can see. And maybe what we see eventually makes the trip worth attempting anyway. The final chapter delivers the verdict on whether the word nearest has any meaning at all. After all of this, after the distance and the speed and the flares and the radiation and the dust and the generations and the bones and the silence, the question comes back to where it started. Why may our nearest star already be too far for humans? The answer, honestly, is yes. With current technology, with current biology, with current civilization, Proxima Centauri is out of reach for any human being alive today. It is out of reach for any human born this century. The wall is too high, the fuel is too weak, the journey is too long. The destination, even if reached, may be a corpse of a planet around an angry star. This is the brutal verdict. Nearest is a word we have used wrongly for over 100 years. Proxima Centauri is nearest the way the moon is nearest. Yes, by the strict numbers it is the closest. But the closest grain of sand on the other side of an ocean is still functionally infinite for an ant standing on this beach. The closest star to Earth is in the same category, only worse. That sounds like despair. It is not. Because the picture has another side. Every year, humans push the wall back. We invent better materials. We build better telescopes. We launch better probes. We learn things about Proxima today that no human knew 30 years ago. We have confirmed planets there. We have mapped the orbit, the brightness, the temperament, the wind. The wall has not moved, but our understanding of it has grown. There is also the small matter of time. Humans, as a species, have existed in modern form for around 300,000 years. Civilization, the kind with cities and writing, is roughly 5 to 10,000 years old. Modern science, the kind that can build rockets and split atoms, is less than 400 years old. The space age is barely 70 years old. In that tiny sliver of 70 years, we have gone from never having left Earth to landing robots on Mars, flying probes past every planet in this system, and pushing 2 voyages into the dark beyond the heliosphere. That is a stunning rate of change. Project that forward, even modestly, and the future does not look like the present. It looks bigger. The Proxima problem may yield in the next century, or the next millennium, or it may never yield at all. None of us today will know. What is certain is this: the dream is allowed by physics. Light travels there in just over 4 years. The trip is permitted, just barely, by the universe itself. Whether humans can ever match that speed, by any means, fair or strange, is the question hanging over the next 1,000 years of our species. If we succeed, we become the first known biology in the local galaxy to step from one star system to another. If we fail, we join the silent majority, every species that ever rose and looked up and could not reach. Either outcome is interesting. In the meantime, on the next clear night, find a dark place, look south toward the constellation of Centaurus. Imagine, hidden between the brighter stars, a tiny red ember, 25 trillion miles away, 4 years of pure light, the nearest star. It is right there. It is also forever.